Good evening. Here we have second lecture, that is revision lecture. Now we have for the continuous beam shown in figure, calculate partial derivative of moment with respect to redundant VB. So we are interested VB as redundant. So we have VB as a redundant for the segment AB and BC. Now we will have to go actually first in last also we have to go this step. So we should have step 1. There also we have to take step 1. We have static indeterminacy. Static indeterminacy. In proper actually we have one only. Now here we have ds E equal to R minus equilibrium equations. So we can write 4 minus 3 and that is equal to 1. Or you can write 3 minus 2 that is equal to 1. We are not going to consider any horizontal. DSI 0 because we have open loop. And then from this we will get value of ds and that is equal to 1 plus 0 and that is 1. So structure is statically indeterminate. Statically indeterminate to degree 1. So indeterminate to degree 1. To degree 1. And this indeterminacy we have external. So we have to consider a reaction as redundant. And then we have step 2. So we have to go for selection of redundant. And here it is given selection of redundant. So here we have given and therefore we have redundant equal to VB. They have already mentioned it. So redundant we have to go as VB. So now we have to go from left or we have to go from right. So now if we will see, we have step 3 now. We will have find VA and VC in terms of VB. In terms of VB. Now, as beam is symmetrical with center, beam is symmetrical with center, symmetrical with center, and therefore VA equal to VC. And therefore, whatever we will write for AB, we have same for CB. So we can write here that is partial derivative for AB and AC is same. AB and AC is same. Now we will find a relation between VA and VB. So we have this as VA. So we will take moment about C equal to 0. And then we have VA into 6 minus 90 into 4.5. So we have first VA into 6, then minus 90 into 4.5, then due to VB plus VB into 3. And then due to this 90, we have minus 90 into 1.5. And that is equal to 0. And therefore, if we will find VA from this, we will get VA that is equal to 90 minus 0.5 VB. So we have this is value of VA. Now knowing value of VA, we can prepare the table and then from that we can find partial derivative. So we will go with, so now I will prepare the table. So we have this as serial number. Then we can have a region. Then we have origin. then limit, then we have M, and then we have dabba M by dabba VB. Now we will go with this table. So now we have first region, that is A to D. Now I will mention this as AD, and then we have this as E. Now we have calculated this reaction VA, and we have this reaction VA 90 minus 0.5 VB. And we have same, this reaction also we have same 90 minus 0.5 into VB. Now we will go serial number, we have 1. So we have 1 region, we have now AD, or I can say AD and CE, we have same values we will get. Origin we have A. If I will consider CE, then I have origin as C. Then limit we have 0 to 1.5, and then M, if I will consider X over here, between A to D, origin is A, then we have this as 90. So we have 90 minus 0.5 VB, and that is into X. And then if we will take derivative, we have minus 0.5 X. Then we have second region. So we have that is DB. So now we have second region DB. Origin we have D. Limit we have same 0 to 1.5. And now we have X, that is from D now. So we have X from D. And then we have this will be now moment is most important. So we have VA. Now VA I will not write. 90 minus 0.5 VB into, now we have to take this distance. And we have this distance, that is X plus 1.5 till this. So we have into X plus 1.5. And then due to 90 we have minus. So we have this distance minus 90 into X. So we have minus 90 into X. And then we have to take derivative with respect to B. And then we will take derivative with respect to B. So we have minus 0.5 into X plus 1.5. And expected is this. If we have this problem in the examination, then we have to go till this. We have to find derivative with respect to B. We need not have to go for calculations to find value of VB. So this is one problem which is from question bank. Then we will have analyzed the continuous beam shown in figure and determine the reaction at B. Then again we will go step 1. We have static indeterminacy. In proper also you can go with this step. So static indeterminacy. What we will get in this? We have ds E equal to R minus equilibrium equation. Now you can go 4 minus 3 equal to 1 or 3 minus 2 equal to 1. ds I equal to 0, open loop. And therefore we can write directly ds equal to 1 plus 0, that is 1. Therefore beam is statically indeterminate to degree 1. Statically indeterminate to degree 1. Determinate to degree 1. Then we have second step 2. Selection of redundant. Selection of redundant. Now we will not go redundant as VB because then we have to find VA and VC in terms of VB. Now as beam is symmetrical with center. Beam is symmetrical with center. Symmetrical with center. Therefore, VA equal to VC. And therefore, we will assume, so consider VA as a redundant. Consider VA as a redundant. And therefore, we will get this also VA. So we will have this as VA. And then this also we have VC equal to VA. So whatever we have M for AB, we have same for CB. Now we will go. So what we have to go for? Then we have, according to Castigliano's second theorem, dabba U by dabba VA, that is equal to 0. And therefore I will write twice. Why twice? Because whatever equation I have from A to B, we have same equation from C to B. There is no change in the equation. So I will make it twice. That is 0 to L M into dabba M by dabba VA dx upon EI. And now I will put it 2 times integration 0 to 3. Now we have this as VA. So we will consider X from here. So we have this as X. And then we will get it as 2 times 0 to 3 VA into X minus 30 X into X by 2 into dabba M by dabba VA. So we will get it as X and whole into dx upon EI, and that is equal to 0. So now try to understand M. So we have, if I will write M, we have that is equal to VA into X minus 30 into X by 2. And then we have dabba M by dabba VA. We have that is equal to X. So this is for your A, B. Now if we will write for CB, then you are going to get same. So we have M. If I will write, this will be X. And we have VA equal to VC. So we will have this also VA. And then we will get same. M is equal to VA into X minus 30 into X by 2. And we will get dabba M by dabba VA. Again same, we will get it as X. And then we have, therefore we will substitute this. So we have this value that is M. So this is M. And this value we have dabba M by dabba VA. And then these two will go on this side, become 0. So now I will make separate 0 to 3 VA I will take outside into X square dx upon EI. So we have this X, we have to multiply both terms. Now this becomes 15. So we have minus integration 0 to 3. You can take 15 outside also, in bracket X cube dx upon EI, and that is equal to 0. And if we will solve this, then we have this will be integration X square from 0 to 3, we will get this as 9 VA, and that is equal to, we have integration X cube from 0 to 3, and we will have this value and multiply by 15. So we have 303.75. And if we will calculate value of VA from here, so we have divided by 9, we will get 33.75 kilonewton. And we know this is equal to VC. VB and VC we have same. And now we will apply summation Fy equal to 0. So we have VA minus 30 into 6 total UDL plus VB, sorry. So we have plus So plus we have VB plus VC, and that is equal to 0. And from this we will get VB is equal to 180 minus 33.75 minus 33.75, and from this we will get value that is equal to 112.5 kilonewton. Therefore, we have a reaction at B equal to, so reaction at B equal to 112.5 kilonewton, and that is obvious. Plus value we got means we have this is upward. So answer we are expected in this fashion. So if we have this problem in the examination, so likewise we have to solve the problems of continuous beam that is related with your Castigliano's theorem. So we have seen problems that is of proper cantilever. Now we have seen problems that is of continuous beam. So now we will stop here only. Other problems we will see in the next lecture. Thank you.